Okay, thanks, Andrea. Yeah, so I was asked to talk about random instances, and then I saw the program and I noticed that I'm only one of two speakers that will talk about this topic. So I decided to take it up on me to try to convince you that random instances are an interesting topic. Yeah, so this will be a brief introduction. So I'll try to give a very high-level survey of these objects that I think are very interesting. And so, okay, this is acknowledge the fact that I have two small kids, so I started learning something. Okay, so you all know what is satisfiability, right? So you have n variables, n Boolean variables, 0, 1, and then you have to you want to satisfy m k clauses. Each clauses is the disjunction of k variables or their negations, okay? And you want to satisfy all of them. And okay, there is of course many versions of this problem that we will talk about. Decision is the resolution, optimization, maximize the number of satisfied clauses over all possible assignment, and counting, that is connected to things that we heard about today, is count the number of solutions of such an instance. Okay. And okay, something that I will use quite a bit through the talk is a representation of an instance as a graph. Okay, so you can think of an instance either as a hypergraph or as a factor graph. So here I gave the factor graph representation. The factor graph is a graph with two types of nodes, nodes that correspond to variables, so Boolean variables, and nodes that correspond, so these are little circles, and nodes that correspond to factors, these are little squares. And I put an edge between a factor and a variable node if and only if that variables appears in the corresponding clause. So for instance, this is my representation of the clause x5, x7, not x9, not x10. Okay? And the dashed edge, I put a dashed edge when there is a negation, and this is a simple formula over n variables and 4 clauses. Okay, so what is standard mainstream complexity theory is about the following question. Is there an algorithm that works well for all instances of this problem? So for all graph G. So often I will denote my instance as a graph. It is understood that this can be a decorated graph, like in my example. So is there an instance that works well for all the instances? Random instances tries to do something different. We define a probability distribution over instances, P of G. And then we ask, is there an algorithm that works with high probability when you draw G from this probability distribution? Okay, okay, so now what works might mean many things, but for instance, finds a solution in this problem with high probability. Okay, so there are many reasons really to be pessimistic about whatever this approach can tell you. And this is why this is not a mainstream approach. First of all, there is many possible choices of this probability measure. Who should tell us which one is the best? Okay, when you start thinking of this, it means that you need to get out of your room and try to model a little bit real instances. So in a sense, you need to model the real world. And if you're just interested in complexity theory, this is something that you don't want to spend time on. Third, it's very important, random instances are not robust to reductions. Beautiful things about complexity theory is reductions. And because of that, it's very difficult to prove, or nearly lower bounds for interesting distribution over random instances. It's very difficult to prove that things are hard in any meaningful sense. It's possible to prove that they are easy, but not that they are hard. So I want to go against this argument and claim that still random instances are interesting, and then I'll come back through this list of motivations at the end of the talk, at the mid of the talk, at the center and the end of the talk. There are some classical motivation, that is why people started studying random instances. And if you look back in papers in the 80s, Typical motivations were, first one is, okay, we have many heuristics for solving satisfiability. We want to compare them. How should we compare them? Just let's throw random instances at them. And the second is a little bit more philosophical. Okay, we know that random instances are, but what are there, exist, but what do they look like? You cannot construct anyone explicitly, so the next best thing is that you can construct them by a probabilistic construction. I'll tell you what are my motivations. They are not this motivation. First motivation is that these are actually often, I claim, good models for problems that are actually important. Okay? And this is becoming more and more so because of the explosion of machine learning, computational statistics, etc. Right? In all of those things, often people come up with statistical model, that is probabilistic model for computational problems, right? And you want to analyze those statistical models, and people work hard for modeling those, and so we should take them seriously. Second, something that has emerged quite clearly over the last 10 years, there is some beautiful mathematics in the theory of random instances that involves probability theory and statistic mechanics. And third, by analyzing random instances, people have come up with nice algorithmic ideas. So one is that we'll talk about a bit is message passing algorithm, local algorithms. There has been actually a lot of work on convex relaxation on all sorts of random instances, and has given a lot of insight. So this is the outline of my talk. I'll give some example and history starting from scratch, then discuss some structural properties, discuss a certain type of models that are related to applications, and they're called planted models, and then computational properties. Conclusions. So some examples. Okay, so this is my picture before for satisfiability. When people started finding how to put a probability distribution, one of the first ideas, now I don't know which one is the very first paper that does this, but it's a pretty old paper, was, okay, I'll draw a formula uniformly at random, or equivalently, I'll draw each clause independently, nearly equivalently, each clause independently among all the possible ones. So how many possible clauses of k variables I can generate, and choose k, because I have to pick the k variables, times 2 to the k, because I can negate or direct each of the literals. Okay? So I sample m clauses independently from this distribution. Okay. So people started studying this, and this was one of the first things that they discovered. Okay, so this is from a paper by Scott Kirkpatrick and Bart Selman, also quite old paper. What they did here is they plotted for several values of k, so 2, 3, 4, 5, perhaps 6. They plotted what? They generating random instances with this distribution and different values of n, and they plotted the probability that that instance admits a solution as a solution. They solved it by some exhaustive method, and this is for some small sizes. And then what they noticed is the following, that take for instance, I don't know, k equals, so we said this is perhaps 6, k equals 6. If you do this for a small values of n, the empirical probability goes from 0 to 1 in a small window around the point. Okay? And then if you take n larger, it goes again from 0 close to 1 in a small window. And if you take n larger, also goes from close to 0 to close to 1 in an even smaller window, and the transition becomes sharper and sharper as n gets larger and larger. Okay? So these three curves are three values of n for the same k. Okay? So this kind of finding led people to formulate the following conjecture, as known as Satisfiability Conjecture. There exists for every k, there exists a critical point of alpha. So what is here, the parameter is the number of clauses over number of variables. There is a critical value of this ratio, okay, such that random instances are satisfiable with high probability below this value, and they are unsatisfiable with high probability above this value. Perhaps I should stop. Does this make sense to everybody? Okay, great. Okay, so this is, I think from the same paper or a similar paper by Kirkpatrick and Selman. They did it more careful for very vast values of n, and for instance, they quote numerically the following approximate value for k equals 3, 4.17. We see that it's not quite right, but it's not too far off. Okay, so this was interesting. So a random formula are not so with some probability satisfiable or some probability unsatisfiable, but they are, depending on the number of clauses per variable, are either mostly satisfiable or mostly unsatisfiable. Okay? Why is that? And the second thing, it was a computational phenomenon that they noticed. This is actually from a popular science paper. Actually, I remember reading this when I was an undergraduate, and this is what got me interested into this whole story. And they solved it with some exhaustive search, and they found it that if you plot the number of operations versus the same parameter alpha, this at small alpha, it's very easy because you have very few constraints. At large alpha is harder, but still not too hard because there is lots of constraints, so you quickly find out that the problem cannot be satisfied. And in between there is a peak, and this peak is very close to this 4.17. So the phase transition was at 4.17, and they found the peak was at the same, roughly at the same position. Again, why is that? Okay. So these two things spurred a lot of work, and we'll talk about it. So I'll use this satisfiability as a running example, but I want to mention two other examples. So one thing that is beautiful about this is that the same theory that is still not there, but is being developed, seems to apply to a huge number of examples. They just behave all the time in the same way. Another example is random graph coloring. You generate an instance of coloring simply as follows. You generate a random graph where n vertices and laying down each edge with the probability d over n. So this is an Erdős-Rényi random graph with bounded average degree. Average degree is d. And then you ask yourself the question, can I find a proper coloring with q colors, where q is bigger or equal than 3, the case q equal 2 is easy. Third example that has some differences from the previous ones, but is still interesting, is random k-XOR SAT. In this case, again, the variables are Boolean, 0, 1, and the constraints, so you have constraint, each constraint involves k variables, and each constraint is really a linear equation over k variables, okay? So you have a set of m linear equation, each equation involves k variables, okay? So the equation looks like this. And the distribution is, again, I sample each equation uniformly at random among all the possible ones. There is n choose k possible ways of choosing the left-hand side and 2 ways to choose the right-hand side, so structure. So in this case, this is a little bit different from the previous ones because, of course, the decision problem and the counting problem are easy, but they are similar in other respects. Okay, structural properties. What I mean by this is the question. First question is, does a random formula have solutions? And following question is, somehow, what does this solution look like? So the main thing that attracted people in this area is, okay, can we prove this satisfiability conjecture? Can we prove that actually random formulae undergo a phase transition? Okay, so a piece of notation. So there is the simplest method to approach this problem is the method of moments. So I want just to explain this because it's really the simplest way of getting bounds. It doesn't get you all the way to the threshold, but it gets you interesting bounds. So how does this work? Okay, the set of solutions. So let's think of a problem with Boolean variables. So the space of possible solution is the Boolean hypercube, 0, 1 to n. The set of solution of a given random formula is a random subset of this hypercube that I will indicate by S, calligraphic S. Okay? So I'll call Z the number of solutions, so the cardinality of this set. And what is the moment method? It's a way to get upper and lower bound. The upper bound is very easy. All right? So the upper bound is what? You want to prove the probability, you want to show that the formula is satisfiable, is unsatisfiable. So you want to upper bound the probability that Z is bigger or equal than 1, that there exists at least one solution. So you do Markov inequality. This is at most the expectation of Z. Now the expectation is Z is what? Is the number of possible assignment of possible 0, 1 vector times the probability that any of this vector is a solution. Now this is just depend on that. The probability that any of this vector is a solution, this is the probability that each clause is satisfied. Since clauses are independent, it's probability that one clause is satisfied raised to power m. What is the probability that a clause of random k-sat is satisfied? Well, the only way you don't satisfy it is that you forbid every single assignment of every single literal, so it's 1 over 2 to the k, the probability that is not satisfied, so this is probability that is satisfied. So this is just, you expand this and you get n log 2 minus n alpha log 2, and you notice that there is an n on front, so this probability goes to 0 as soon as this term beats this term. So this implies that when alpha is bigger than 2k log 2, this goes to 0, so alpha s is smaller than 2k log 2. Okay? So this is simple upper bound. So remarkably it took a while even to match the 2 to the k in this expression. Okay? So I'll go ahead with the moment method. So you want to prove a lower bound. So you want to lower bound the probability that Z is bigger or equal than 1. Now by a kind of fancy named variant of Cauchy-Schwarz. This is lower bounded by the expectation of Z squared divided by the expectation by the second moment. Now we like to prove that this goes to 1. An important simplification is that it is sufficient to prove that this is bounded away from 0. Namely, if you know that P of Z bigger or equal than 1 is bounded below by some delta positive, then you know also that limit as n to infinity P of Z bigger or equal to 1 is equal to 1. Okay? So this is not an easy fact. It's a consequence of a theorem by Friedgut that shows the following. It doesn't show that this satisfiability property has a sharp threshold. Okay, it doesn't prove that it has a phase transition as a precise point, but it proves that it has a sharp threshold around a value alpha s that can eventually depend on n. Okay. So, a random formula pass from satisfiable to unsatisfiable in a very small window, around the threshold that can depend on n. Okay? So, because of that, as if you know that this is bounded away from 0, then you know that you are below this threshold. Okay? So, it's sufficient to prove to get an upper bound. A lower bound on alpha s, on the satisfiability threshold, sufficient to prove that the second moment is upper bounded by some constant independent of n times the square of the first moment. Okay? So you can try to do that, and we can try to do the calculation for satisfiability. I will not do it in the interest of time, it's not hard. But one interesting thing is that it doesn't work for k-sat. Right? Now this is a method that is so simple nowadays that there are a billion of reasons why it doesn't work. Okay, but I will start from one of these reasons. So the reason why when the second moment matches the square of the first moment, it means that. So okay, let's look what is the second moment. the second moment, the expectation, the second moment is the sum over all x and y of the probability that x and y satisfy my random formula. Okay, let's call the random formula C, whatever it is, right? So while the first moment when you do this calculation, you realize that the case in which the second moment is the square of the first moment is when the x and y that dominate the sum are the pairs x and y that are basically they are uncorrelated. Okay, they are independent. If you look at the joint type of these two vectors, so the number of vertices where they are 0, 0, 0, 1, 1, 0, 1, 1, this joint type, the empirical distribution of these two vectors, factorizes. When this phenomenon happens, then the product, the second moment, becomes closer to the square of the first moment. Okay? So this happens when this sum is maximized over pairs xy that whose type is factorized, is independent. Right? So this doesn't happen for K-SAT. Why? Well, it doesn't happen for K-SAT because of the following. If you take a random formula, a variables in this random formula might be directed. Remember the graph representation. So remember that I indicated by a dashed line every time that a clause is negating that variable, and a continuous line every time that a clause is having that variable in directed form. Right? So this variable in this special small formula that I draw is directed in all the clauses that it belongs to. So you expect that if you take two random solutions, the value of this variable will be correlated because it will tend to be true in both random solutions. Right? So simply because of this local bias, for K-SAT there is no value of alpha in which this happens. So if you do this, not only you don't get a good bound, but you get no bound whatsoever. Okay, so for fixing this, the trick that was used, the idea that was used was to change the definition of Z. Right? I want to prove that this Paley-Zygmund inequality is true about any random variable Z. It has to be non-negative, but it's true for any random variable Z, right? So you want to take a random, if you take a random variable that is, you want to take a random variable Z that is positive as soon as the formula is satisfiable. And you want to get rid of this problem of the local bias, of the fact that in most solution, this variable will take value true. Okay? So the first way that people, Kleoptas and Moore, found to solve, go around this problem was the following. Instead of counting the number of solutions, I count the number of not all equal satisfying solutions. Okay, so I don't count number of solutions, but I count the number of assignments that satisfy each clause and satisfy also the opposite of the same clause. Where the opposite of a clause, I mean the clause that is obtained by that by changing each literal in its negation. So in other words, for each clause, if this is a clause appearing in my formula, I want my assignment to be a special type, not only to satisfy this clause, I want it to satisfy also this clause. So in a sense, I'm shooting myself in the foot, right? Because I'm not, there might be a lot of satisfying assignments, but a lot less of not all equal satisfying assignment. So I'm shooting myself in the foot. But what I'm gaining is the fact that now I'm canceling the bias. I'm canceling this type of bias here. Okay? In fact, if you do this calculation, they were able to do this calculation, and you got a bound that is roughly a factor 2 below the real satisfiability, below the upper bound. Okay, so they got for the first time the factor 2 to the k, but they got a factor 2 in front wrong. Okay? This because they basically they doubled the number of constraints that we were trying to satisfy. All right? A smarter idea was used in a paper by Kleoptas, Naur, and Perez. What they did is, okay, I don't need to be so cruel, just satisfy, each clause and its opposite. What I'll do is just construct a weight that kind of fights against this natural bias. So the natural bias for a random solution is to go in the direction of the majority of the literals that it belongs to. Instead, I put here a number smaller than 1 raised to the number of literals satisfied by x. So not all solutions are created equal. There are some solutions that satisfy a lot of literals, some solutions that satisfy less literals, and I look for the solution that satisfy less literals because those solutions are less prone to this bias. Now, it's not obvious, but it's a result of the calculation that if you take this exponential weight, now this will, save my random variable and make the second moment work up to, a non-trivial threshold. And in particular, in this way, they were able to prove that alpha s is between 2 to the k log 2 minus k and 2 to the k log 2. Okay. So this was about second moment and rescuing the second moment method by this problem. Okay. To move beyond this, the step forward, beyond this kind of moment method came from statistical physics. And a crucial idea was that, okay, you have to really understand this satisfiability phase transition, you have to understand somehow the geometry of the space of solutions. It's not enough to study every single solution, but to understand how they are related. Okay? And turns out that this was related, you can think about your geometry in another way. You can think instead of, so by geometry of the space of solution, what I mean is the following. We'll talk about it a bit more. This is a random subset of the Boolean hypercube. Its geometry is a subset of this metric space. Okay? But turns out that in the physics intuition, this was related to another theme that is, okay, if you look at the uniform measure of a solution, what are its spatial mixing properties? I will not talk about this in any detail, but the two are closely related in the physics theory. So how much correlation there is between variables in a random solution. So it turns out that using these ideas and method from statistical physics in 2002, Mézard, Parisi, and Zecchina were able to compute exactly, give exact conjectures for the threshold of random k-sat. In particular, for k equal 3, this gave you this number 4.2667. Now this the real physics theory has a formula for this. It's a formula that takes a few slides, so perhaps one slide. So I am not brave enough to copy it here, but as you see, this is in the right ballpark and was conjectured to be exact, not approximate. If you remember, the numerical calculation was 4.17. Okay, so for talking about this issue with the geometry, I want I have to set a couple of definitions. So again, variables are in 0, 1. So let's do the following. Fix a scale. So this is a distance that tells me whether two solutions are close or far apart. This is a scale L of n that goes infinity with n. So I will take it to be small of n. Okay? And then for any two solutions, I will say that they are close if their Hamming distance is below this scale. And then what I'll do is simply I'll take the set of solution and quotient it by this equivalence relation. Quotient it by the closure of this equivalence relation. All right, so this gives me a partition of the set of solutions into clusters. The equivalence relation is not really this, is the closure of this. So two solutions are related if there is a path between that with step of this size. Now this is a bit, this definition is a bit tricky because, okay, you have to fix this scale. This might seem arbitrary, but somehow in the cases that are well understood, there is basically any value of this scale that you take makes sense. The maximum Hamming distance is n, and basically anything because between polylog and n over polylog gives the same partition, basically. And the picture that emerged from these papers is, okay, more or less the following: that depending on alpha, three scenarios happen. Alpha is the fraction of the closest pair variable. Above the satisfiability threshold, that there is no solution, but then there is two more phase transitions, and they correspond to the following. Below this, that is called the dynamical or clustering or shattering phase transition, there is basically only one equivalence class in this partition. Between this dynamical and the second phase transition, that I'll call the condensation phase transition, there is exponentially many equivalence classes. So solutions get shattered or separated in small clusters that are well separated. And in this final interval, there is only order 1 of these clusters, but more than one, actually a random number. So this is normally very confusing, so I will try to explain it more formally, okay, these three scenarios. Okay. So what I mean by this is the following. Take these clusters and order them by cardinality. So you have C1, C2, Cn. So then the following happens. In the first regime, C1 takes a fraction for any epsilon. So all of these are statements that are conjectural to hold with high probability. So C1 takes 1 minus epsilon times S for any positive epsilon. So as all the mass, there can be some powder out there, but it's all of it. In this interval, to make all the mass, you have to put together a big bunch of guys. And how many you have to put them together? You have to put together exponentially many, e to the n sigma. And each of them has basically the same size, takes up a fraction e to the minus n sigma. And finally, somehow the most, the final regime, then the following happens. Think of putting together the first q clusters for any fixed q, and compute what fraction of the total mass this makes. Okay. In the first case you will get 1. In the second case you will get 0. In the third case you get a random variable that is a non-degenerate random variable. It's something that is strictly between 0 and 1, and there's a well defined distribution. Okay? So it's like when you take a piece of bread and you break it at a random point, then you take what is left on one side, on the right side, and you break it at a random point, and then you take what is left and you break it at a random point, etc., and then you order your pieces of bread. You get pieces of bread of order 1, but random size.
Andrea, in the second case, what's the quantification? Like, what is? You should say like for every m naught, if you want the summation to be more than 1 minus epsilon times s, m needs to be at least that much?
Well, it's not for any m naught. There exists m naught and m, where m is of this side, where this happens, right?
But
so m naught, I want to, okay, I could do the following. I take a from the largest up to m. I could have stated in this way. There is, take all the cluster from the first one to the mth one. This would make this mass. There would be still this many. M naught is much smaller than this, but they would not be all of equal size. Okay. So in other words, there can be a few ones that are much bigger. So the typical size of a cluster is this one. If you take a random solution, typically it happens to be in a cluster of this size. Okay? It's like I take my stick and then I break it in some big pieces, but still small of one. Then I break most of it in exponentially many pieces, all of the same size. So those big pieces are bigger than the rest, but they really do not matter. If you take a random point in the interval, it will happen to be in one of the small pieces.
So there exists M naught, M and sigma, such that 1 minus epsilon fraction of S is contained into sets of size roughly e to the...
Sets of this size, all the sets in this, there exist M clusters where M is of this order, and they are all of this size, and they make up 1 minus epsilon of all the, Now, there exist also bigger clusters.
But they don't add up to too much of...
they don't add up too much. And in fact, there is a whole, as you imagine, it's not that there is big and small, there is a whole distribution of them. All right, so this is the picture that emerged in these physics papers and was entirely non-rigorous, and over years people have proved parts of this. So there is one special case in which you can prove a lot of things very precisely, and this is cakes or sat, because since it's a linear system, all clusters have equal size. So people proved basically everything that you might want. You might always want to know more, but all of this picture. But it's considerably simpler in the sense that, as you write, in the sense all the clusters are equal and there is no phase, no intermediate phase here. So this condensation phase coincides with the phase transition here. So it's a simpler case because of linear algebra. In case satisfiability, there are partial results in the sense that these are and in Q coloring partial result. So in what sense these are partial? And in the sense that they are typically they hold for large enough K or large enough number of colors, and they typically get bounds on alpha S and alpha C, and so they don't get sharp threshold for this phase transition, and they typically. Sometimes they give you the number of clusters and sometimes not. So for instance, this result gives you a sharp result on the number of clusters, but for instance, this result doesn't give you a sharp result on the number of clusters. Okay. So for instance, to be concrete, for small k, the question is open, or another question is open is typically prove that these clusters are internally connected, well connected. It's easier to prove that they are well separated, but that they are connected internally is more difficult often. Okay, so now this might seem a long digression, this on the geometrical space of solution. We started with doing something very concrete, counting the number of solutions, or this satisfiability threshold, and now I did this whole digression into what is the geometry of the space of solution. The point is that this was crucial in also getting a rigorous result for this threshold. Okay, so I explained to you that the second moment method fails because this kind of local biases that induces correlation. In general, the second moment method fails when two random assignment two typical assignments that contribute to this sum are uncorrelated. Okay. But if you think at this intermediate regime, now think of drawing two random assignments from the uniform measure over solution. They will typically, or with positive probability, fall in the same clusters. So they will be correlated. So there will be, under the uniform measure, there will be a positive correlation. Now, the measure that you get when you get second moment is even a worse measure, but this suggests that in this interval, no matter how you painfully improve your second moment method by constructing carefully your random variable, you will be in trouble. In particular, what happens in this regime is that the typical value of the number solution is much smaller than the expectation of the number of solution. And this is true even if you truncate this expectation. Typically, when this happens, what people do is put here an indicator over the local structure of the graph, but this doesn't cure this problem in that regime. All right, so again, there are, we can go on and on in discussing the intuition of this, but this is what I described just now. Okay, so the idea to overcome this is the following. What you should do is not count the number of solutions, but count the number of clusters. Okay? And this turns out that have, again, in the physics picture, many other characterization. For instance, there are a number of fixed points of this algorithm that I'll discuss in a minute, belief propagation, a number of fixed point of a certain whitening process. So the whitening process is a process that takes a cluster and shrinks it down to a point, recursively replacing each variable that can take both 0 and 1 value by a star. So in a sense, assignment 0, 1 star to the end that is, collapses a cluster in one point. So these kind of ideas were present in a very, non-rigorous way in the physics literature. For instance, in this paper there was some description of this whitening procedure, but they were really made rigorous in the work of Amin Kojaoglan and Zhang, Nike, and Alan Lai. Okay? And in particular, this is a key step in proving this theorem by Dingsla and Son, that is, for all k large enough, random k-sat has a threshold, so this proves the satisfiability threshold, and again is given by this physics prediction that I will not write down. And the key, it's a very complicated argument, but one key ingredient is do the second moment method, but counting the number of clusters and using as a proxy for cluster these whitened solutions. Okay, now I'm late on time. So I want to discuss two more things. One is planted model, and the other is computational implications. All right, so what are planted models? So far what we did is that we generated the random formula, basically uniformly at random. There is another way that is very interesting, is the following. You first generate one solution, one vector in your space, one assignment, and then you generate the formula uniformly at random, conditional on that being a solution. For instance, in the case of coloring, you draw a vector in the space uniformly at random, and then you draw an instance uniformly conditional on X being a solution of that instance, uniformly among all graphs that have the same number of edges. And then you can do the same for planted k-sat, etc. Okay. So there is an interesting way of describing this. You can think of this generation of a planted assignment as the following. I have a vector that is my coloring, my hidden coloring, that I want to communicate to you. And the way I will communicate it to you is that I will give you a list of clauses that are generated by that process. Okay, so I generate a vector, but I don't give you the vector. I generate clauses at random from the distribution uniformly at random, conditional of being clauses that are satisfied by that assignment, and then I give you these clauses to you. Or I generate edges from this graph uniformly at random, subject to connecting vertices of different color, and I give this list of vertices from you. So the problem then is that you can ask is, can you count the number of possible messages that are compatible with the output? This is the counting problem. Or the decision problem is there. What is the optimization problem is find the original thing. And there is a connection. So this is, for instance, the expectation of log z, the number of solution, is the conditional entropy of x given y. Now, this kind of problem has also its own phase transitions that are closely related to what I talked before. And at high level, what happens is that to this picture of clustering, you add one cluster that contains the transmitted solution. Now, why I want to elaborate on this planted ensemble is that the reason I want to elaborate on this is that a lot of interesting models from information theory, machine learning, statistics, etc., fit in this framework. Okay, and here I list a few. for instance, compressed sensing, network analysis, matrix factorization, etc. Okay, I will not put any references. Okay, but interestingly, this thing that is random case out or coloring of random graph that was initiated as a just a conceptual game turns out to be closely related to all sorts of models that are studying these applied areas. Okay, so I hope I convinced you of these two. This turns out to be connected with models that are important for applications in this area, and they contain some beautiful mathematics. I want to spend perhaps 10 minutes talking about this, right? So far we started with, we wanted to solve hard distances or understand hard distances, but we didn't talk basically about computation at all. So I want to talk about computation. Okay, there is a long history of people that did the following. Take your favorite heuristic that is simple and easy to state, etc., and analyze how it behaves of a random formula. Okay, and often these heuristics were based on simple iterative procedures that modify the graph, and a popular method to analyze it is the ordinary differential equation. So you prove that these heuristics follow a Markov, the evolution of these heuristics can be described by a low-dimensional state space and follow a Markov chain and find a large n limit for this Markov chain, and this gives you the analysis. So this is a long list of papers, but so this is a very interesting kind of work, but it's somehow you can go on forever, right? You can every time come up with a slightly smarter heuristic and try to analyze it, and this will be more and more difficult and will get you, bound on the satisfiability threshold, etc., etc. But for a while there didn't seem to be a unifying concept. Okay, and I think that the unifying concept in this area is again comes in some sense from physics, and is related to the following idea. Okay, so let's say that we are talking about coloring. For a fixed vertex I call ball IT the ball of radius t center at that vertex I. And now I can talk about these two objects. The first one, mu ig, is the marginal distribution of variable xi when x is a uniformly random assignment among all those that are proper coloring. So imagine of doing conceptually the following. I sample a proper coloring for my graph. Okay, this is assignment of all coloring of all the vertices, and then I compute the marginal of the color of this coloring on vertex I, the distribution of the color of vertex I. This is mu ig. If I know how to compute this, I'm the king, right? Because by a similar argument to what Nayantara talked about today, earlier, I can count the number of solutions if I can compute marginals, and I can also find solution for theory. But okay, of course, this is difficult to do, but what I can try to do is the following. Take the space of the set of solutions that satisfy the subgraph induced by the ball. If you look at the set of vertices that have distance at most t from I, this induces a graph, so you can look at a proper coloring over their graph, pick one uniformly at random, and compute its marginal. And the intuition is that, okay, first of all, if things are nice and t is large but not too large, it should be true that this marginal, the thing that you want to compute, is close to the one that is obtained by sampling from the ball. If this happens, then things are great, because this kind of marginals over the balls can be computed very quickly. Okay? The simplest way to compute it, the stupid way to compute it, is just you take the ball of size epsilon times n, and then you generate colorings from this ball, But then you realize that in these random graphs, what happens is that if you look at the ball of size epsilon times log n, of radius epsilon times log n, is with high probability a 3. Right? And computing marginals for a uniform distribution over coloring of a tree, it's just a simple dynamic programming operation. So it can be done in time that is linear in the sides of the ball. So I can go over every single vertex, look at the ball of radius epsilon n, compute the induced marginal at the center, and use that as an estimate of my marginal. Okay? So this has a name. It's called belief propagation in artificial intelligence. And actually can be done much more quickly than that. If you think a little bit, it can be done in time that is of order number of edges times t using these local tree-like properties. But that is not crucial for what I'm talking about. So this is this belief propagation algorithm. It's looking at all balls and computing the induced marginal at the center. Now, how do you use this for finding solutions? This is one possible way to do it. Is okay. You repeat the following. You have a running set S that are the vertices that have not been decided so far. At the beginning, no vertex has been decided, so S is equal to V. And then you repeat the following. Look at the graph induced by S, so the graph that contains S. Compute the corresponding marginals. And then, for instance, take a vertex in that set uniformly at random and fix the variable to a value xi star that is drawn from this distribution. And then, eliminate this from the graph. Okay, I write it a little bit succinctly. I should do a little bit more, because if I fix one variable to red, the neighboring variable, that node is not eliminated. The neighboring variable cannot be red. But you understood the idea. You reduce the graph in some way, and reduce the coloring problem to a least coloring problem. So if these marginals were the exact marginals under the uniform distribution on this graph, so if this index t was not there, what this algorithm would do is something beautiful. It would generate a uniformly random coloring. So instead of doing this, I'm doing a myopic version of this thing, and I'm generating this thing. Okay, so now the question is, if you try to do this, so this is an algorithm that in some sense encompasses and unifies many heuristics, because it uses in optimal way the local information on the graph, but doesn't go beyond the local information. So when does this happen? If you look again at this phase diagram, okay, I don't have really time to explain why, but what should happen is that this is a grouped approximation outside this regime. So if you are below this condensation phase transition. And this again has been proved in special cases and in special models. Okay? So this what suggests to for the behavior of this algorithm. First of all, it will not work well here. It might work well here, but not necessarily, because in the process of reducing the graph, I'm deforming my graph, I'm deforming my instances, so I might undergo another condensation phase transition. So there is another axis that is somehow time, and as time evolves, these clusters are reduced, and you might undergo another phase transition. And okay, this we put forward in a paper a few years ago, and there is a few papers that confirm this picture. In particular, Amin Kojoglan has an analysis of this BP-guided decimation and proves that it has a threshold that for large k behaves like 2 to the k over k. Okay? So this algorithm, so 2 to the k over k is over here, and this is consistent with this heuristic that we gave a few years earlier. And Amin Kojoglan has another algorithm that has the best existing guarantee of any algorithm, polynomial time algorithm for finding solution in a random case out, and works below 2 to the k log k over k, that again is in the same regime. It's related to this first dynamical phase transition. Now, in the same work in which they computed the satisfiability threshold, Mézard, Paris, and Zekila had an improvement over this idea, a significant improvement over this idea. They demonstrated that work quite a bit better, substantially better for k equal small k. So they did k equal 3, and then Selman and others did simulation for 4 and 5. And the idea, so what they called it is survey propagation instead of belief propagation. And the idea here is, you can think it in different way, but one way to think about it is that instead of doing the computing the uniform distribution, considering the uniform distribution over solution, again you consider the uniform solution over clusters. Okay? Again, each cluster can be somehow uniquely identified by a 0-1 star assignment or 0-1 question mark assignment. And so you do this 0-1 star assignment, the uniform measure is approximately described by Markov random field on the same graph, and so you work with that instead than with the original thing. And okay, finally there is a general argument by Gamarnik and Sudan that suggests that this 2 to the k log k over k is probably a threshold for any local algorithm, any algorithm of this type that look at a bounded neighborhood and then operates on the basis of that. So I say suggest because they have a theorem that is for not all equal SAT, not for SAT. Okay, perhaps 1 minute. There is something that I didn't talk about. Okay, just 1 minute. There's another side of the word is optimization, right? So what happens on this side when you want to maximize the number of satisfied assignment? And for instance, in this case, it's interesting already and simpler to study XOR SAT. So you take a random XOR SAT instance, and okay, the terminology that people use is the following. So what you want to obtain is an algorithm that provides a strong refutation, ideally. That is the following: an algorithm that is polynomial time and that gives you always an upper bound on opt, on the optimum value. This optimum value is between 0 and 1. 1 means that you can satisfy everything. And you want that this algorithm gives you at most 1 minus delta with high probability on random instances. So it strongly refuses random instances. Right? So if you come from so this is a theory application. It's not an application. You can think that you want to use this for the following game. Somebody gives you a formula, and the formula can be either a random k-XOR SAT formula or a planted random k-XOR SAT formula. Okay, in this case it's easy. But you want to decide between these two hypotheses. Now, in this case, it's easy because XOR SAT is the linear structure, but you can do the same for SAT and other things. Okay, so many people studied this, and using SDP relaxation, and for instance, proved the following: that okay, for getting a refutation, so being able to get even such a loose approximation on the opt, you need the number of clauses to be at least n to the k over 2. Right? So if you remember this experiment in which you have computation time that then slowly go down, this is telling that it will hit polling time at number of clauses n to the k over 2 instead of n. All right? And on the other side, there is a reason to believe that there is no algorithm that will work below this n to the k over 2, in particular because the sum of square hierarchy cannot do it. Okay, so this is work by several people. Just put it together in one theory. Okay, so I hope that I convinced you that. Okay, this is models for many applications. There is some interesting mathematics and also some interesting ideas. So if I have to look forward, so one the class of model on which people made a lot of programs are in the physics language are this problem with 1RSP, in which there is this clusters of solutions that are well defined. There are problems that are somehow considered more complex, and one example is max cut, in which the geometry of the space of nearly optimal solution is conjecturally even more complex. Okay, we don't yet know the satisfiability conjecture for small k. We know fairly little about counting. So I talked about decision and I talked about optimization, but the picture about counting is even fluer. And okay, it would be nice to get somehow sharper analysis of SDP relaxation for this problem. That's all. Thank you.
Questions? I wonder, do we know something about the geometry of the solution space of, say, monotone K CNF? So monotone, no negation of variables.
No
negation. All connected, right?
All connected?
I mean, the solutions are all, the solution space is connected here, because all one is a solution. But
yeah, I don't know of any result. I would expect that, first of all, it's always satisfiable. And second, I would, my guess, if you draw a random formula for this, so something that is studied a lot in physics is the ferromagnetic Ising model. So probably, or another, probably one can think it as an analogous of the ferromagnetic Ising model. So, yeah, so I would expect that in particular monotone, there is no this clustering phenomenon, but I don't want to swear it because I would expect that this phenomenon doesn't appear there.
Could you comment on how you come up with these very precise predictions about sizes of clusters as a physical prediction?
Yeah, so one way to do it, so in this regime, so really one way to do it is, so there is one prediction, so one way to understand it is the following. Okay, so let's start. First thing is how you come. So people have a very precise prediction of the number of solutions here, right? The prediction is of this type that 1 over n log z, and this goes Zn being the number of solutions of random. This is a random variable, goes to some phi, and there is a formula for phi. So how you come up for a formula for this phi? Okay, it takes a few hours to describe, but one idea is the following. You suppose of adding one single clause, okay, or one single variable. So you can think of this z and m, so the number of solution for n variable m clauses. So you try to compute these two type of thing, and if you know what is the limit of this, then you are king. Okay. So how you compute this? Well, you start thinking a little bit, or you look at this. This is what, for instance, I'm taking is the probability. So call this the uniform probability distribution over solution for a random formula with n variable and m clauses. This is the probability that whatever, that the clause, the new clause is satisfied. So you want to compute with respect to a random formula the probability that if I throw a clause, this is satisfied. Okay. So this is what is related to. So I draw a random clause, and then there will be the rest of the graph that was here before. If I know what is the joint distribution of these 3 or k vertices, then I'm done. Now I can try to compute this joint distribution simply by locally this graph. So this is the graph G and M. I can compute this joint distribution by not looking at the whole graph, but looking only at a ball of radius t. So I can hope to do this calculation because for any fixed t, this will be a 3. So I get a 3 recursion that will give me the 3 things, and then will give me this, and then I plug here, and I get a formula. So you do this gymnastics. It's not completely trivial, but you get a formula for all this regime. The formula at a certain point breaks down here, but before that there is this clustering phase transition. So how do you deal with it? So well, the way you deal with it is the following. You know, in this regime, what happens is that the total number of solution is still given by this guy, this kind of formula, but then you take a random assignment, a random coloring, and compute the number of solutions that are close to this. So this corresponds to repeating this calculation, but putting a different boundary condition at the bottom of the tree. You see, once you do this, this computation gives you this number in terms of a solution of a recursion on a tree. Right? Now, it might happen that this if you're lucky, this recursion has a unique solution, you're happy. Sometimes it's multiple solutions. Often it's 2 solutions, and this corresponds somehow to, there is a strong correlation between the boundary and the center of the tree, or there is weak correlation. So this gives you 2 values. Phi, let's say correlation, let's call it phi in and phi tot. So phi tot is the one that you obtain with the weak correlation, boundary condition. So you initialize the solution with a weak correlation here, and fin you initialize with a strong. And then you interpret this, okay, and in some cases all of this can be, remember this as the real number of solution, and here the number of solution inside a cluster. And therefore the log of the number of cluster is phi tot minus phi. It's the number of solution divided by solution of cluster, so the logarithm subtracts. So it's somehow mysterious that all of this can be carried out, but
We should stop here. Thanks again.